Unit 2, Matter and Energy. The objectives. After studying this unit, you should be able to define matter, list the 3 states in which matter is commonly found, define density, discuss Boyle's law, state Charles' law, discuss Dalton's law as it relates to pressure or different gases, define specific gravity and specific volume, state 2 forms of energy important to the HVACR industry, describe work, and then state the formula used to determine the amount of work done by performing a given task, define horsepower, convert horsepower to watts, and convert watt hours to British thermal units, BTUs. 2.1 Matter. Matter is commonly defined as a substance that occupies space and has mass. The weight of a substance is the combined effects of a substance mass and the force of gravity pulling down on it, whereas weight equals mass times gravity. Matter is made up of all the atoms. Atoms are often described as the smallest amount of a substance and may combine to form molecules. Atoms of one substance may combine chemically with those of another to form a new substance. These new substances are referred to as compounds. The molecules formed cannot be broken down any further without changing the chemical nature of the compound. Matter exists in 3 states: solid, liquids, and gases. The heat content as well as the pressure exerted on matter determines its state. For instance, water is made up of molecules containing atoms of hydrogen and oxygen. 2 atoms of hydrogen and 1 atom of oxygen are each in each molecule of water, figure 2.1. The chemical formula for water is H2O. Water in a solid state is known as ice. It exerts all of its force downward. It has weight. The molecules of the water are highly attracted to each other, figure 2.2. When the water is heated above the freezing point, it begins to change its liquid into a liquid state. The molecules' activity is higher, and the water molecules have less attraction for each other. Water in a liquid state exerts a pressure of outward at a 90-degree angle and downward. Because water pressure is proportional to its depth, water seeks a level surface where the pressure is equal to that of the atmosphere above it. Figure 2.3. Water heated above the liquid state, which is 212 degrees at standard conditions, becomes a vapor. In the vapor state, the molecules are even less attracted to each other, and vapor exerts a pressure equally in all directions. The study of matter leads to the study of other terms that help understand how to define how different substances compare to each other. 2.2 Mass and weight. Mass is the property of matter that responds to the gravitational attraction. Weight is the force of that matter, the solid, liquid, or gas, applies to a supporting surface when it's at rest. Weight is not a property of matter, but is dependent on the gravitational attraction here on Earth. The stronger the force of gravity, the more an object will weigh. The Earth has a stronger gravitational attraction force than the Moon. This is why objects weigh more on Earth than on the Moon. All solid matter is mass. A liquid, such as water, is said to have mass. The air in the atmosphere has weight and mass. 2.3 Density. The density of a substance describes its mass to volume relationship. The mass contained in a particular volume is density of that substance. Sometimes it's advantageous to compare different substances according to weight per unit of volume or pounds per cubic foot. Water, for example, has a density of 62.4 pounds per cubic foot. Wood floats on water because the density, the weight per volume, of wood is less than the density of water. In other words, it weighs less per cubic foot. Iron, on the other hand, sinks because it is more dense than water, figure 2.5 up here. So if this number is less than 62.4, it will float. If it is bigger than 62.4, it will sink. And all of these look like they are bigger than 62.4, so they're all going to sink. These are typical densities. Can you figure out why ice floats on water? Oh, there's your exception. That does not have the density higher than 62.4, so therefore it's got less density, and it floats. At least 80% of it does, or 20% of it. 80% is underwater. 2.4, specific gravity. The specific gravity, unitless number that, because it really is the density of the substance divided by the density of water. So we're using water as a comparison. That's 62.4. Water is simply used as a standard comparison. The density of water is 62.4 pounds per cubic foot. So the specific gravity of water is 1, because if you divide 62.4 divided by itself, 62.4, that's 1. So any number less than 1, it's going to float. So the units cancel each other because of the division. The density of red brass is 548 pounds per cubic foot. Its specific gravity is then 548 pounds per cubic foot divided by 62.4 pounds per cubic foot, which leaves us a gravity number of 8.7. Because this number is bigger than 1, it's going to sink. So figure 2.5, that's where they get these specific gravity numbers from. Take 171, divide it by 62.4, and that gives aluminum a specific gravity of 2.74. So it's not as heavy as brass or copper or any of the other metals here that are listed, but it is still heavier than water, and it will sink. Specific volume. Specific volume indicates the volume that each pound of a gas occupies. The measurement requires that there must be only 1 pound of the gas, and the units are expressed in cubic feet per pound, which differs from the units for total volume, which are simply cubic feet. 1 pound of clean dry air has a total volume of 13.33 cubic feet at standard atmospheric conditions. So that means its specific volume would then be 13.33 cubic feet per pound. As the air is heated, it becomes lighter, and its specific volume increases as it expands. As the air is cooled, its specific volume decreases as it contracts. Hydrogen has a specific volume of 179 cubic feet per pound under the same conditions. Because more cubic feet of hydrogen exist per pound, it has a higher specific volume. Thus, it's lighter than air. Although both are gases, the hydrogen has a tendency to rise when mixed with air. Natural gas is explosive when mixed with air, but is lighter than air and also has a tendency to rise like hydrogen. Propane gas is another frequently used heating gas, but it has been treated differently than the natural gas because it's heavier than air, so it sinks. Propane has a tendency to fall and collect in small, low places and pose a potential danger from ignition. When volume and density are considered inverse of one another, this means that the specific volume equals 1 divided the density, and that density equals 1 divided by the specific volume. If one knows the specific volume of a substance, its density can be calculated, and vice versa. For example, the specific volume of dry air is 13.33 cubic feet per pound. Its density then would be 1 divided by 13.33 cubic feet per pound, and that means each pound has a weight, the air of each pound of air has a weight of 0.075 pounds per cubic foot. Notice that even the units are inverses of each other. Substances with high specific volumes are said to have low densities, and other substances with high densities have low specific volumes. Density and specific volume are inverses of each other. Multiplying the density of a substance by its specific volume will always yield a product of 1. The specific volume of air is a factor in determining the fan or blower horsepower needed in the air conditioning work. As an example, A low specific volume of air requires a blower motor with higher horsepower, and higher specific volume of air can utilize a blower motor with a lower horsepower rating. The specific volumes of variations pumped gases is valuable information that can enable the engineer to choose the size of compressor or vapor pump to do a particular job. The specific volumes for vapors vary according to the pressure the vapor line is under. And as the pressure of the gas increases, the specific volume of the gas decreases or its density increases. As the pressure of the gas decreases, the specific volume of the gas increases and its density decreases. So there's always a relationship there. And these gas laws kind of highlight that. It is necessary to have a working knowledge of gases and how they respond to pressure and temperature changes. Many years ago, several scientists made significant discoveries about these properties. A simple explanation of gas laws they developed may help you understand the reaction of gases and the pressure, temperature, volume relationships in various parts of the refrigeration system. Whenever using pressure or temperature in an equation like the gas laws, one has to use the absolute scales of pressure, PSIA, and temperature, which will be Rankine or Kelvin, or the solutions to these equations will be meaningless. Absolute scales use 0 as their starting point because 0 is where molecular motion actually begins. Boyle's law. In the early 1600s, Robert Boyle, a citizen of Ireland, developed what has become known as Boyle's law. He discovered when pressure is applied to a volume of air that it contained, that volume of air becomes smaller and the pressure greater. Boyle's law states that the volume of a gas varies inversely with the absolute pressure, provided that the temperature remains constant. For example, if we have a cylinder down here with a piston at the bottom of it, and it's closed off at the top, and we have it filled with air, and the piston moves halfway up the cylinder, the pressure of the air will double. In this figure 2.6. The part of the law pertaining to the temperature remaining constant keeps Boyle's law from being used really in practical situations. This is because when the gas is compressed, some heat is transferred to the gas from the mechanical compression. And when the gas is expanded, heat is given up. However, this law, when combined with another, becomes practical to use. So we look at this. This is the formula for Boyle's law. And what it says is P1 times the volume of 1 equals the pressure, number 2, times the second volume. So where P1 is your original absolute pressure and V1 is your original volume, once you change one of these, you'll have a new pressure and you'll have a new volume. So for example, if the original pressure was 40 pounds per square inch absolute and the original volume was 30 inches cubed, what would the new volume be if the pressure was increased to 50 pounds per square inch absolute? We're determining the new volume then. So the formula would have to be rearranged so that we could find the new volume. And that's what we're looking for, volume number 2, which equals pressure number 1 times volume number 1, and that'll be divided by pressure number 2. So we had 40 pounds per square inch absolute times 30 cubic inches, and we're going to divide that by 50 pounds per square inch. So these will cancel each other out. And really what you're looking at is 1,200 divided by 50, which is our volume 2 of 24 cubic inches. So our volume dropped by 6 cubic inches, and the pressure went up by 10 psia. That's how we use this formula. Now Charles came along a couple hundred years later, and in the 1800s, a French scientist named Jacques Charles made discoveries regarding the effect of temperature on gases. Charles' law states at a constant pressure, the volume of gas varies directly as the absolute temperature, and at a constant volume, the pressure of a gas will vary directly with the absolute temperature. In other words, stated in a different form, when a gas is heated, it will expand, and if it can do so, to expand. And the volume will vary directly as the absolute temperature if a gas is confined in a container that will not expand and is heated. The pressure will vary directly with the absolute temperature. This law can also be stated with the formulas. Two formulas are needed because one part of the law pertains to pressure and temperature and the other part to volume and temperature. So he had two different formulas. So this formula pertains to the volume and temperature. And what this says is the volume of the original volume 1 divided by the original temperature will equal the second volume divided by its temperature, the new temperature, where V1 is our original volume and V2 is going to be our new volume. T1 is our original temperature and T2 is our new temperature. So we use this in heating for sizing ducts. If we have a 2,000 cubic foot air being passed through a gas-fired furnace and it's heated from 75 degree room temperature to 130 degree Fahrenheit, what is the volume of the air leaving the heating unit? So we have to first change our numbers to absolutes, which is adding 460 degrees Rankine to 75 degrees, and we get 535 degrees absolute. We're looking for the new volume number 2, and we know that the temperature leaving the furnace is 130 degrees plus 460 degrees Rankine gives us a temperature of 590 degrees absolute. So we're going to rearrange the formula too so that we have, really is what we're looking for is that one there. So we need to get this one over here, and we do that by putting V1 times T2 is going to be divided by our first temperature. So if you've got 2,000 cubic feet times 590 degrees Rankine, the temperature of the air leaving the furnace, and you're dividing that by our 75 degree room temperature converted to absolute, we're going to get a volume of air needed exiting the furnace of 2,205 about cubic feet. So the cubic footage went up about 200, and this result shows here what happens in this figure. And then this formula up here pertains to the pressure and temperature relationship. So this was temperature and volume, and now we're dealing with a pressure-temperature relationship, and this is the basis for our PT chart that we use with our refrigerants. So we have one pressure, our original one, and we divide that by our temperature that pressure is a relationship with, and we're going to get a new pressure when we change the temperature in some way of a new temperature. So if we have a large natural gas tank and it's holding 500,000 cubic feet of gas stored in 70 degrees, and the spring temperature rises to a 95 degree day in the summer, that means that gas is going to want to expand, and we need to make sure that we got enough room for it to expand or the correct vessel that can handle the new pressure. So what would the new pressure be if the original pressure was 25 pounds per square inch gauge in the spring? So we've got to convert both our temperatures and pressures to absolute, which means we're going to add the atmospheric pressure of 14.69 psi to our 25 psi gauge reading that we got for the original reading. And we're going to add our 70 degrees to 460 degrees to get 530 degree absolute temperature. We're looking for our new pressure, but we know our outdoor temperature in the summertime is 95 degrees Fahrenheit. We're going to add 460 degrees to that, and that's going to give us 555 degree absolute. We rework the formula because this is what we're looking for, pressure 2. So that's going to leave us pressure 1 times temperature 2 divided by our first temperature, temperature 1, which gives us our 39.69 pins per square inch absolute times 555 degrees Rankine, and that number we're going to divide by 530, and then we're going to convert the pressure back to gauge pressure. So we're going to take our 41 pounds per square inch absolute and minus about 14 psi, which gives us a new pressure of 26.87 psi. Gee, doesn't really go up that much. Talking about 1.8, almost 2 psi G with this temperature change, so that's not a big deal. So later they combined the two laws and they formed the general law of perfect gas. PV equals MERT, pervert. That's what a lot of people call this. And this is a general gas law, often called the general or law of perfect gas. It's a combination of both Boyle's and Charles' law, and this combination law is more practical because it includes temperature, pressure, and volume all in one. And the formula for this law can be stated by the pressure of the first pressure times its original volume divided by its original temperature will be equal to the second pressure times its new volume divided by its new temperature, where P1 is original pressure, V1 is original volume, T1 is original temperature, P2 is our new pressure, V2 is our new volume, and T2 is our new temperature. For example, if we have 20 cubic feet of gas and it's being stored in a container at 100 degrees Fahrenheit and it has a pressure of 50 psig, and the container is connected by a pipe to one that will hold an additional 30 cubic feet for a total volume of 50 feet cubic now, and that gas is allowed to equalize between the two vessels or containers, the temperature of the gas is lowered to 80 degrees. What's the pressure of the combined containers? So we've got to do some math here first. We're going to have to convert the psig to atmospheric, which is adding the atmospheric pressure, which is giving us the absolute of 64.69 psia. We've got our volume, which that's standard, 20 cubic feet. And our temperature we're also going to convert to absolute, 100 plus 460 Rankine gives us 560 absolute. We're looking for our new pressure. We got a new volume of 50 cubic feet, and we have a temperature now of 80 degrees plus 460, which is 540 degrees Rankine. So we're going to plug all these numbers into the new formula after we rearrange the formula to find P2 is going to equal P1 times our first volume times our new temperature. And we're going to divide that by our old temperature at our new volume, multiplied our new volume. So we have 64.69 psia times our 20 cubic feet times 540 degree absolute temperature. And when we divide that by 560 degrees Rankine and our new volume of 50 cubic feet, then we will find that we get 24.95 pounds per square inch absolute for our pressure. And to convert that back to gauge, that's going to drop the pressure down to 10 psig once it equalizes on both containers. So we can see what happens when the volume goes up, the pressure goes down, and the temperature goes down, because our new temperature now is 80 degrees. So we have got Dalton's law. And Dalton, think of dual pressures. If you got two different pressures, we're just going to add them together. Two different gases, dual gases, we're just going to add them together and get the sum of the two. So John Dalton is an English mathematics professor, and he made the discovery in the early 1800s that the atmosphere is made up of several different gases. He found that each gas created its own pressure, and the total pressure was the sum of these individual pressures. Often called Dalton's law of partial pressures, or Dalton's law, states that the total pressure of a confined mixture of non-reacting, which we call inert gases, is the sum of the pressures of each of those gases in the mixture. For example, if I got a cubic foot of nitrogen and I got a cubic foot of oxygen and I placed both into one cubic foot container, and then the pressure on the container is going to be the addition of, as if both these were in itself added together. So you got the 30 psi here, and you add the 30 in the container, and you mix in the 40 psi of nitrogen, and that gets added on top of the 30 for a total pressure reading on the gauge with a mixture of 70 psig. So you just add the two together. The mixture of the two is the total pressure. Energy. Using energy to properly operate equipment is a major goal of the HVACR industry. Energy in the form of electricity drives the motors. Heat energy from the fossil fuels of natural gas, oil, and coal heats the homes and industry. What is energy and how is it used? The only new energy we get is from the sun heating the earth. Most of the energy we use is converted to usable heat from something already here, for example, fossil fuels. This conversion from fuel to heat can be direct or indirect. An example of direct conversion is a gas furnace, which converts the gas to usable heat by combustion. The gas is burned in a combustion chamber, and the heat from combustion is transferred to circulated air by conduction through the thin steel walls of the furnace's heat exchanger. The heated air then is distributed throughout the heated space, which is this figure right here. An example of indirect conversion is a fossil fuel power plant. Gas may be used in the power plant to produce the steam that turns the steam turbine generator to produce electricity. This electricity is then distributed by the local power company and is consumed locally as electric heat, which is going to be figure 2-10. 2.8 Conservation of energy. The preceding sections of this unit lead to the law of the conservation of energy. This law states that energy is neither created nor destroyed, but can be converted from one form to another. It can thus be said that all energy can be accounted for. Most of the energy that we use is the result of the sun's support of plant growth for millions of years. Fossil fuels come from decayed vegetation and animal matter covered by the earth and rock during changes in the earth's surface. This decayed matter in various states, such as gas, oil, or coal, depending on the conditions it was subjected to in the past. This energy stored in fossil fuels is called chemical energy because a chemical reaction is needed for it to release the energy. Energy contained in the heat. Temperature is a measure of the degree of heat or heat intensity, but not necessarily the amount of heat. Heat is a form of energy because of the motion of the molecules. To be specific, heat is thermal energy. If two substances of different temperatures are moved close to one another, heat energy from the substance with the higher temperature will flow to the one with the lower temperature. Figure 2-12 here. So 100-degree heat flow to 75-degree, warmer to cooler. That's the second law of thermodynamics. This was the first. This is the second. Heat will always flow from warmer to cooler. Because the molecular motion doesn't really stop to negative 460 degrees, energy is still available in any substance, even at very low temperatures. So like here you have negative 200 degrees Fahrenheit. That still has more heat than something that's negative 350 degrees Fahrenheit. So heat will still flow until they both equal out and go into equilibrium with the same number. Most of the heat energy used in homes and industry is provided from fossil fuels, but some comes from electrical energy as shown in figure 2-10. Electron flow in high-resistance wire causes the wire to become hot, thus heating the air. So they're running some electricity through the heating element in the wire, and that's causing the air to warm up as it blows over it. A moving airstream is then passed over the heated wire, allowing the heat to be transferred to the air by a condition and moved by conduction, forced conduction, and moved to the heated space by forced convection. Okay, so the air is touching the heated wire, that's conduction, and the air is being forced by the blower, so that's forced convection. Energy and magnetism, 2.10. Magnetism is another method of converting electron flow to usable energy. Electron flow is used to generate magnetic fields that are in turn used to turn motors. The motors turn the fans, pumps, and compressors that ultimately move the air, water, or refrigerant. In figure 2.13, an electric motor turns a water pump to boost the water pressure from 20 to 60 psi G gauge. So it's 20 psi G coming in, and the pump is spinning, which increases the pressure of flow out to 60 psi G. This takes energy, so the energy in this example is purchased from the power company. The preceding examples serve only as an introduction to the concepts of chemical energy, heat energy, and electrical energy. Each subject will be covered in detail later. For now, it's important to realize that any system furnishing heating or cooling uses energy. 2.11. The purchase of energy. Energy must be transferred from one owner to another and accounted for. This energy is purchased as a fossil fuel or as electric power. Energy purchased as a fossil fuel is normally purchased by the unit. Natural gas is an example. Natural gas flows through a meter that measures how many cubic feet have passed during some time span, such as a month. Fuel oil is normally sold by the gallon, coal by the ton. Electrical energy is sold by the kilowatt hour, or kWh. The amount of heat each of these units contains is known, so a known heat content of about 1,000 BTUs per cubic foot. The heat content of oil number 2 is about 139,000 BTUs per gallon, and there are numerous types of coal available, and the heat content can range from 14 million BTUs per ton of coal up to over 26 million BTUs per ton of coal. 2.2. Energy used as work. Energy purchased from electrical utilities is known as electrical power. Power is the rate of doing work. Work can be explained as a force moving an object in the direction of force. So it is expressed in units called foot-pounds or foot-pounds. It is expressed by this formula. Work is determined by the force times distance. So force is expressed in pounds and distance is expressed in feet. For instance, when you have a 150-pound man climb a flight of stairs 100 feet high, which is about a 10-story building, he performs work, but how much? The amount of work in the example is equivalent to the amount of work necessary to this man of the same height. We can calculate the work by using the preceding formula. So he did about 150 pounds of labor, because that's what he weighs, moving up 100 feet, which means he did the equivalent work of 15,000 foot-pounds. Notice that the time frame has to be considered. This example can be accomplished by a healthy man in a few minutes, but if the task were accomplished by a machine, such as an elevator, more information would need to be necessary. Do we want it to take seconds, minutes, or hours to do the job? The faster the job is accomplished, the more power that you're going to need, or is it required. 2.13 Power. Power is the rate of doing work. An expression of power is horsepower. Many years ago, it was determined that the average horse could lift the equivalent of 33,000 pounds to the height of 1 feet in 1 minute, which is the same as 33,000 foot-pounds per minute, or 1 horsepower. This describes the rate of doing work because the time factor has been added. Keep in mind that lifting 330 pounds to a height of 100 feet in 1 minute, or if you're lifting 660 pounds to a height of 50 feet in 1 minute, that's going to require the same amount of power. As a point of reference, the blower motor of the average furnace can be rated at half a horsepower. So that means it can do about the same amount of work as this guy here. If this guy could have ran up those stairs in 1 minute, we can put the time with that, and that's half of that. When the horsepower is compared with the man climbing the stairs, the man would have to climb 100 feet in less than 30 seconds to equal 1 horsepower. That makes the task seem ever so harder. A half a horsepower motor could lift that man 100 feet in about 1 minute, only if the man were lifted. The reason that 15,000 feet per pound of work is required, because remember, you got 33,000 of foot-pounds of work for 1 minute, that equals 1 horsepower. So that's about half of that. That's why we can get away with half a horsepower motor. Our purpose in discussing these topics is to help you understand how to use power effectively and to understand how power companies determine their methods of charging money for power. Electrical power, 2.14, the watt. The unit of measurement for electrical power is the watt. This is the unit expressed by power companies, used by power companies. When you get your energy bill, you pay for kilowatt hours, which is the cost for using 1,000 watts of power for 1 hour. When converted to electrical energy, it takes 746 watts to equal 1 horsepower's worth of work. Fossil fuel energy can be compared with electrical energy, and one form of energy can be converted to another. There must be some basis, however, for conversion to make the comparison. The examples we use to illustrate this will not take efficiencies for various fuels into account. Efficiencies of fossil fuels will be discussed in the corresponding units of this text. Examples of conversions follow. So we can converting electric heat rated as kilowatts to the equivalent gas or oil heat rated in BTUs per hour. So suppose we want to know the capacity in BTUs per hour for a 20 kilowatt electric heater, and we're going to replace it with a gas furnace. And we know that a kilowatt is 1,000 watts. So we're looking at 20,000 watts of electric heat. And if we know that 1,000 watts or 1 kilowatt is equal to 3,413 BTUs per hour, we can then multiply our 20,000 watts by 3,413 BTUs, and we get a number of 68,260 BTUs of heat energy needed to match that 20 electric kilowatt heater. If we want to convert BTUs to kilowatts, if we want to figure out how much something's going to cost us from the electric company to operate, suppose we got a gas or oil furnace and it has an output capacity of 100,000 BTUs. Since we know that 3,413 BTUs per hour equals 1 kilowatt, we have 1,000 BTUs divided by our 3,413 BTUs per kilowatt equals 29.3 kilowatts. In other words, a 29.3 kilowatt electric heating system will be required to replace the 100,000 BTU per hour furnace, and vice versa up here. Contact your local utility company for rate comparisons because different fuels have different costs. So, to summarize, matter takes up space, has mass, and can be in a form of solid, liquid, or gas. The weight of a substance at rest on the earth is proportional to its mass. Density is the weight of a substance per cubic foot. And specific gravity is the property used to compare the density of various substances. Specific volume is the amount of space of a pound of a vapor or gas that it will occupy. Boyle's law states that the volume of a gas varies inversely with the absolute pressure provided the temperature remains constant. And Charles' law states that at a constant pressure, the volume of gas varies directly to the absolute temperature. And the constant volume, the pressure of a gas varies directly with the absolute temperature. Dalton's law stated that the total pressure of a combined mixture of non-reactive gases is the sum of the pressures of each of the gases in the mixture. Electrical energy and heat energy are two forms of energy used in the HVACR industry. Fossil fuels are purchased by the unit. Natural gas is metered by the cubic foot, oils purchased by the gallon, and coals purchased by the ton. Electricity is purchased from the electric utility company by the kilowatt hour. Work is the amount of force necessary to move an object. In other words, work equals force times distance. And a horsepower is the equivalent of lifting 33,000 pounds to a height of 1 foot in 1 minute, or some combination totaling the same. Watts are a measurement of electrical power, and 1 horsepower equals 746 watts. 3.413 BTUs per hour equals 1 watt, and if you have 1,000 watts, then that equals 3,413 BTUs. Review questions. Number 1. Matter is a substance that occupies space and has A. color, B. texture, C. temperature, or D. mass. Number 2. What are the 3 states in which matter is commonly found? Number 3. Blank is the term used for water when it is in solid state. 4. In what direction does a solid exert force? 5. In what direction does a liquid exert force? 6. Vapor exerts pressure in what direction? A. Outward, B. Upward, C. Downward, D. All the above. 7. Define density. 8. Define specific gravity. 9. Describe specific volume. 10. Why does an object weigh less on the moon than on Earth? 11. The density of tungsten is 1,210 pounds per cubic foot. What would be its specific volume? The specific volume of red brass is 0.001865 cubic feet per pound. What would be its density? Aluminum, number 13, has a density of 171 pounds per cubic foot. What would be its specific gravity? 14. 4 pounds of a gas occupy 10 cubic feet. What would be its density and its specific gravity? What is the information regarding the specific volume of gases? Why is the information regarding number 15? Why is information regarding the specific volume of gases important to the designer of air conditioning, heating, and refrigeration equipment? 16. Whose law states that the volume of gas varies inversely with the absolute pressure, as long as the temperature remains constant? A. Charles, B. Boyle's, C. Newton's, D. Dalton's. 17. At a constant pressure, how does a volume gas vary with respect to the absolute temperature? 18. Describe Dalton's law as it relates to a confined mixture of non-reactive gases. 19. What are the two types of energy most frequently used or considered in this industry? 20. How were fossil fuels formed? 21. Blank is the time rate of doing work. 22. State the formula for determining the amount of work accomplished in a particular task. 23. If an air conditioning compressor weighing 300 pounds had to be lifted 4 feet to be mounted on a base, how much work in foot-pounds must be done? 24. Describe horsepower and list the quantities needed to determine horsepower. 25. How many watts of electrical energy are used and equal to 1 horsepower? Number 26. How many BTUs of heat can be produced by 4 kilowatts of electricity? 27. How many BTUs per hour would be produced in a 12 kilowatt electric heater? 28. What unit of energy does the power company charge the consumer for? 29. If 3,000 cubic feet of air is crossing an evaporator coil and it cooled it from 75 degrees Fahrenheit to 55 degrees Fahrenheit, what would be the volume of air in cubic feet exiting the evaporator coil? 30. A gas is compressed inside a compressor cylinder. When the piston is at the bottom dead center, the gas is initially at 10 psig at 65 degrees Fahrenheit and has a total volume of 10.5 cubic inches. After compression, though, when the piston is at top dead center, the gas is at 180 degrees Fahrenheit and occupies 1.5 cubic inches. What would be the new pressure of the gas in pounds per square inch absolute? Thank you for listening if you're still here.